The next topic that we want to cover is the measurement of heat using a calorimeter. A calorimeter is a device that allows us to be able to measure a heat change by measuring temperature change between a system and surroundings. So a generic calorimeter will have a vessel where the reaction can take place, and it will be surrounded by a medium that has something like water, for instance, where the heat change or the temperature change can be monitored. So as your reaction takes place in a calorimeter, heat is either given off or is absorbed by the system, and as it does so, you will have an increase or a decrease in temperature as a result. You can then translate that increase or decrease in temperature to a heat measurement if we know the heat capacity of the calorimeter or calorimeter constant, as we will see in just a few minutes. So I just showed you an example of a calorimeter, but the definition now for practical purposes is calorimetry is a measurement of heat changes. Heat changes are measured in a device called a calorimeter, and we just saw an example of that. As we talked about earlier on when we started talking about processes that are measured under either constant pressure or constant volume, we know that there are a different set of conditions that separate constant volume measurements from constant pressure measurements. When we have a constant volume measurement, the volume is not allowed to change and therefore is constant volume. And so this is an example here of a constant volume calorimeter. A constant volume calorimeter is called a bomb calorimeter. The bomb calorimeter is a device that has a sample inside a reaction vessel, like I described earlier. As the sample undergoes whatever reaction it's going to undergo, there is a net increase or decrease in temperature in the surroundings, and the thermometer can show that change in temperature. Since this is a constant volume measurement, the heat transfer that we get from a constant volume or bomb calorimeter is going to be the heat under constant volume, which is the same thing as the internal energy. So whatever heat transfer we get from bomb calorimetry is equivalent to measuring the internal energy. Heats of combustion, the amount of heat that accompanies the burning of some organic substance in the presence of oxygen to generate carbon dioxide and water, those heats are commonly measured in a bomb calorimeter. On the other hand, if we have a constant pressure process, we use other types of calorimeters. And one of the most common types of calorimeter that we can use very easily is a coffee cup calorimeter, and that's what we've done in the lab. In the coffee cup calorimeter, we know that the reaction mixture pretty much is taking place in the whole cup. We measure the change in temperature that we get from the process, and from that we can report a heat after we do the appropriate calculations, and that heat is measured under constant pressure conditions, so therefore the heat that we measure is equivalent to the measurement of the enthalpy value. So when we do constant volume calorimetry, or use a bomb calorimeter, the heat that we're measuring is equivalent to the internal energy. But when we use a constant pressure process like we do in the lab using a coffee cup calorimeter, the heat that we measure is equivalent to the enthalpy. Okay, so the measurement of heat using a calorimeter is a two-step process. Step one is we have to determine the heat capacity of the calorimeter. This is also known as the calorimeter constant. So basically, this is the same thing as the measurement of heat capacity in any other calculation. The heat capacity is equal to the amount of heat that we put through the calorimeter divided by the change in temperature. Now, when we determine the calorimeter constant, we do so in a way that the process that we calibrate the calorimeter with, we do so in a way that we can actually know what that heat input is going to be. We do this calibration for a known heat input. And we can do that in a couple of different ways. The first way is by using the combustion of a standard or known substance like benzoic acid. And this is the type of calibration that we see, the standardization that we see for bomb calorimeters for the most part. So a combustion of a substance with a known heat output. The second is by flowing current through the calorimeter, or through the medium that we're going to measure the temperature change in. The third is the way that we've done in lab, which allows us to estimate the calorimeter constant by estimating the heat lost from a mixture when combining substances at two different temperatures. Well, let's just go ahead and say what it is. When we combine water at two different temperatures, we can measure or estimate the amount of heat that was lost in that transfer, like we did in the lab. So let's just go ahead and say estimate the heat loss from a mixture when combining water at two different temperatures. Okay, so we've got 3 different ways to measure this Q. For purposes of your studying, I want you to focus on these 2. This last one, we will concentrate on the measurements for that one in the lab. Make sure you can read all of this. That's going to be a hard stretch, I'm sure. All right, so now, so one thing that I want to mention here in this one, in number 2, where we say by flowing a current through a medium, I want to give you that equation. So if we flow a current I at voltage V for time t, that allows us to get a measurement of Q that we can use to determine our calorimeter constant. And let me give you the units. The units of I are supposed to be in amps, of V in volts, and time should be in seconds. So a amp times a volt is the same thing as a coulomb, and a coulomb second is the same thing as a joule. So when we complete a calculation that involves a measurement of current measured in amps, voltage measured in volts, and time measured in seconds, our resulting unit should be joules. Oops. The second step in measuring the heat transfer for a reaction using calorimetry is to use that calorimeter constant that you just calculated Okay, we're going to use that calorimeter constant and compute the value of Q for the reaction of interest. All right. Okay, so we've got step 1 where we measure the calorimeter constant. Step 2, it's difficult to read when I have to write a lot on the slides. I do apologize for not having this already printed. But step 2 is use the calorimeter constant to compute the value of Q for a reaction of interest. All right, in order for this to make sense, we're just going to take an example.